In the last equation, we were trying to solve the Laplace equation for the temperature field in a spherical coordinate system, 1 by r square partial by partial r of r square partial t by partial r plus 1 by r square sin theta this is equal to 0. And we had separated t is equal to some function of r and some function of theta. And we had identified that for our problem, in the limit as r goes to infinity, for r going to infinity, t in the matrix is equal to t prime times z. Okay. So, that was an inhomogeneous condition as r goes to infinity. Therefore, the inhomogeneous direction is r and the homogeneous direction is theta. So, we substituted this into the equation, divided throughout by f times g, multiplied throughout by r square, in order to get 1 over f, okay, d by dr of r square df by dr plus 1 over g sin theta of sin theta dg by d theta. This is equal to 0. Okay. And both of these have to be constants, equal in magnitude and opposite in sign, so that they sum to 0. Because the theta direction is the inhomogeneous direction, we expect that constant in the theta direction to be negative. Is equal to minus alpha, where alpha is a negative number. Therefore, I got plus alpha times g, this was equal to 0. Substituted psi is equal to cos theta and d psi is equal to minus sin theta d theta. And the equation becomes d by d psi of 1 minus psi square into dg by d psi plus alpha times g equal to 0. Okay. Alternatively, d square g by d psi square minus psi square d square g by d psi square minus 2 psi dg by d psi plus alpha g is equal to 0. In order to solve this, we had written g as a series. Okay. In this, I will use the index L, psi power L, L is equal to 0 to infinity, instead of n in the previous lecture, so that I can retain the integer n for the eigenfunctions. Okay. So, I will just make this small notational change. I will call it a summation of a l times psi power l. Okay. Substitute that into the equation. Okay. Summation l is equal to 0 to infinity. When I take two derivatives, I get l into l minus 1 a l psi power l minus, okay, summation of, I am sorry, psi power l minus 2. Okay. L into l minus 1 a l into psi power l minus 2 is the second derivative. Then I have the second term here, where basically I am subtracting the first term multiplied by psi square. So, I get summation L is equal to 0 to infinity L into L minus 1 a l psi power l, okay, because I am multiplying it by L psi square, okay, the second term. okay, minus summation of 2 into psi into the first derivative. Okay. First derivative is L psi power 2 L A L psi power L minus 1, that is the derivative, into psi, okay, into this psi here. Okay. So, this just becomes equivalent to psi power L. Okay. Okay, plus alpha summation of A L psi power L, this is equal to 0. In all cases, L is equal to 0 to infinity. Okay. And then what we had done in the first term is to re-express, okay, L prime is equal to L minus 2, okay, which implies that L is equal to L prime plus 2. Okay. Okay. So, for L is equal to 0 and L is equal to 1, this term is identically 0. It starts only at 2, because for L is equal to 0 and L is equal to 1, it is equal to 0. Okay. So, if I substitute L is equal to L prime plus 2, I will get summation L prime is equal to 0 to infinity of L prime plus 2 into L prime plus 1 A L prime psi power L prime, okay, minus summation, okay, L into L minus 1, okay, plus 2 L, okay, A L psi power L plus alpha summation L is equal to 0 to infinity A L psi power L, this is equal to 0. Now, in this I can substitute L prime is equal to L, because it is a summation index anyway. It does not matter which index is summed over, what you call it, because in the end the result will be independent of what you have called that particular index. It only depends upon the range over which the summation is taking place. Okay. So, if I will get summation L is equal to 0 to infinity L plus 2 into L plus 1 A L psi power L minus summation L is equal to 0, please note a correction here, this should be L prime plus 2, okay, because L is equal to L prime plus 2, okay, as noted here, L is equal to L prime plus 2. Therefore, here as well I should have, when I change L prime to L, I will have A L plus 2 psi power L. L into L minus 1 plus 2L is L into L plus 1. This is equal to 0. Now, I can combine the terms that multiply equal powers of L. Okay. I can combine all of the terms that multiply equal powers of L. L is equal to 0 to infinity, okay, of psi power L. Okay. L plus 2 into L plus 1 A L plus 2 minus L into L plus 1 A L plus alpha A L. This is equal to 0. This equation has to be satisfied for any value of L. Okay. This equation has to be satisfied for any value of L. That means that this term within the square brackets has to be equal to 0 for each value of L. Okay, this term within the square brackets has to be 0 for each value of L. Okay. This gives us an equation for A L plus 2 in terms of A L. A L plus 2 is equal to L into L plus 1 A L, okay, minus alpha into A L by L plus 2 into L plus 1. Okay. So, this basically gives us A L plus 2 in terms of A L plus 1. Okay. by sigma A L psi power L. Okay. For psi is equal to 1, G is equal to sigma A L. Okay. For psi is equal to 1, G is equal to summation of just A L. Okay. It is just equal to summation of A L. Okay. And you can see as L becomes large, okay, as L becomes large, I can divide numerator and denominator by L square. So, I will get 1 into 1 plus 1 by L minus alpha A L by 1 plus 2 by L into 1 plus 1 by L. Okay. And in the limit as L becomes large, this is just equal to A L for L becoming large. Okay. And clearly, if A L plus 2 is equal to A L, that means I have a series in which all the terms are equal, and therefore, this series does not converge at psi is equal to plus 1, okay, or minus 1, depending upon whether the L's are alternating or whether they are, okay, of the same sign. Okay. So, it will not converge at psi is equal to plus or minus 1. Okay. And therefore, the temperature field is not well defined at theta is equal to 0, cos theta is 1, or theta is equal to pi, cos theta is equal to minus 1, okay, with this series. Okay. Note that in this series, of course, I am defining A L plus 2 in terms of A L. Okay. A0 and A1 are two unknown constants. Once you know what is A0 and A1, you can get A2 in terms of A0, A3 in terms of A1, and so on, okay, A4 in terms of A2, and so on. Okay. So, you can get all the higher order terms in terms of the lower order terms. Okay. So, you can get A3 in terms of A1, A4 in terms of A2, and so on. A0 and A1 will effectively be determined from the boundary conditions, because when you solve a second order differential equation, there will be two unknown constants. Okay, when you solve a second order differential equation, there will be two unknown constants, both of which have to be determined from the boundary conditions. So, once you know A0 and A1, you know what is A2 from A0, A3 from A1, and so on, and the entire series is defined, except that this little problem that we have here, okay, that A L plus 2 is equal to A L for A L becoming large, and therefore, the series does not converge at psi is equal to plus 1 or minus 1. Okay. So, what do we do in this case? Okay. The only way the series will converge is if for some value of L, okay, for some value, okay, for some value L is equal to n, okay, if A L plus 2 is equal to 0. Okay. If A L plus 2 is equal to 0, for some value of L, some value of the integer L, if A L plus 2 is equal to 0, that means that A L plus 4 is also equal to 0, A L plus 6 is also equal to 0. The series terminates at that value L is equal to n. How will the series terminate? Okay. Only if it will terminate at L is equal to n, only if n plus 1 into n minus alpha is equal to 0, or if this alpha has discrete values n into n plus 1. Okay. Only if this alpha has discrete values n into n plus 1, where n is an integer. Okay. So, if this eigenvalue is n into n plus 1, then for that particular value of n, a n plus 2 is 0, a n plus 4 is 0, and so on, and you get a finite solution. Okay. So, if n is odd, if for example, if n is odd, then you can you have A0 and A1. So, you substitute A0 is equal to 0, A1, A3, A5, etc., until An, where An is odd. At that point, the series will terminate. Okay. So, if n is odd, okay, you will have coefficients A1, A2, etc., An, and at that point it will terminate. Therefore, I can set A0 equal to 0 and get a finite series. Okay. Alternatively, if n is even, okay, I will get A0, A2 etc. An, and the series will terminate, and I will get a convergent series if I set A1 is equal to 0 in addition. So, either you will have an odd series or you will have an even series. If n is odd, you will have an odd series. If n is even, you will have an even series. Okay. In either of these cases, the solution converges. Okay. You will have A0 plus A2 x square plus A4 x power 4 etc. That is one series, that is the even series. Alternatively, you will have A1 plus x plus A3 size cube plus A5 psi power 5 plus etc. Okay, that will be the even series. So, the basic point here is that this Legendre equation has a finite solution only if alpha is equal to n into n plus 1, where n is an integer. Only if alpha is equal to n into n plus 1, where n is an integer. Okay. And the solution of this equation are what are called the Legendre polynomials. Okay. G is equal to P n of cos theta. Okay. For the eigenvalue n, where alpha is equal to n into n plus 1. Okay. If n is odd, this is an odd series, it has cos theta, cos cube theta and so on. If it is even, it is an even series, 1 cos square theta, cos power 4 theta etc. Okay. So, that is for the theta coordinate. What about for the radial coordinate? Okay. So, what I have solved so far is 1 by g sin theta is equal to minus n into n plus 1. Okay. Alpha was negative, okay, in this particular case, because the boundary conditions were homogeneous. Okay. So, now I have to solve for the other part. Okay. Note that the constants were equal in magnitude and opposite in sign. So, I have to solve for the other part, that is d square by dr square, sorry, okay, 1 by f, 1 by of r square df by dr is equal to plus n into n plus 1. Okay. Or d square f by dr square plus 2r df by dr minus n into n plus 1 f is equal to 0. Okay. Yeah, expand this out, multiply by f on the right hand side and expand out the derivative. You get d square r square d square f by dr square, I am sorry, there should be an r square here, d square f by dr square plus 2r df by dr minus n into n plus 1 into f is equal to 0. So, that is the solution for f. This has net 0 dimension in r. Okay. You have r square d square by dr square, r times d by dr, and the third term has no r in it. So, therefore, I can write f is equal to a power of r power alpha. Okay. I can write f is equal to r power alpha. So, first term will get r square alpha into alpha minus 1 r power alpha minus 2 plus 2 r alpha r power alpha minus 1 minus n into n plus 1 f, this is equal to 0. Okay. Into, I am sorry, there should be an r power alpha, f is r power alpha. Okay. Okay. So, this becomes alpha into alpha minus 1 plus 2 alpha minus n into n plus 1 into r power alpha is equal to 0, and you can easily verify this is equal to alpha into alpha plus 1, okay, minus n into n plus 1. This has to be equal to 0. Therefore, alpha is equal to n is one solution and alpha is equal to minus of n plus 1 is the second solution. If alpha is equal to minus of n plus 1, alpha plus 1 is minus n and you get n into n plus 1. Okay. Therefore, f is equal to a r power n plus b by r power n plus 1. Okay. So, that is the solution for the f part. And the final solution for the temperature is equal to a r power n plus b by r power n plus 1 p n of cos theta. Okay. This satisfies the equation, this solution satisfies the equation, and it satisfies the symmetry condition in the theta direction for any value of n. So, the most general solution is of the form summation n is equal to 0 to infinity a n r power n plus b n by r power n plus 1. That is the solution. I will talk a little bit more about p n of cos theta, the Legendre polynomials. These Legendre polynomials also satisfy the orthogonality relation. Okay. So, first of all, p n of cos theta, okay, is equal to a polynomial, or rather let me just write in terms of the psi itself. Okay. P n of psi is equal to a polynomial of order n. Okay. It is a polynomial of order n containing only alternate terms. Okay. That is, if n is equal to an odd number, let us say n is equal to 21, it contains only alternate terms. It contains psi power 21, psi power 19, psi power 17 and so on up to psi power 1. If it is even n, then it contains only alternate terms, that is n is equal to 0, 2, 4, 6 etc. up to n. Okay. So, it contains only alternate terms. Okay. Therefore, for odd n, p n of psi is a or rather let me just write this as, okay, for odd n, okay, p n of minus psi is equal to minus p n of psi. Okay. P n is an odd function of psi, and for even n, since it contains only even functions, p n of psi is equal to p n. Is equal to minus p n of psi, sorry, plus p n of psi. Okay. For even n, this is equal to plus p n of psi. Note that psi goes from minus 1 to plus 1, corresponding to theta going from 0 to pi. Okay. So, this is an odd function of psi, and this is an even function of psi. Okay. So, for odd n it is an odd function of psi, and for even n it is an even function of psi. Okay. Now, there is some ambiguity about how you choose the constants, because if some particular p n satisfies the equation, you multiply that by a constant that will still satisfy the equation, because the equation is linear in p n. Okay. The Legendre equation is a linear equation. Therefore, any solution can be multiplied by a constant and you will still get a solution. Okay. Okay. So, these the Legendre polynomials as we classically know them are normalized. Okay. such that Pn of plus 1 is equal to Pn of minus 1 is equal to 1 for even n, okay, and Pn of plus 1 is equal to minus Pn of minus 1, which is 1 for odd n. So, for odd n, Pn is 1 at psi equals 1 and minus 1 at psi equals minus 1. For even n, Pn is 1 at psi equals 1 and 1 at psi is equal to minus 1. Okay. So, that is the normalization that is chosen for defining these Legendre polynomials. Okay. And once you identify these normalizations, these also satisfy orthogonality relations. Okay. That is integral minus 1 to 1 d psi Pn of psi Pm of psi. Is equal to 2 delta m n by 2 n plus 1. This is the normalization condition that is satisfied for the Legendre polynomials. Okay. Alternatively, I can write this in terms of theta. Okay. Integral 0 to pi. Integration has to be sin theta d theta in a spherical coordinate system. Okay. Pn of cos theta, Pm of cos theta is equal to 2 delta mn by 2n plus 1. So, this is the orthogonality relation in terms of theta, and this is the orthogonality relation in terms of xi, which is cos theta. So, these Legendre polynomials, they satisfy orthogonality relations. These orthogonality relations depend upon this definition. Okay, upon this normalization, okay, upon this normalization that Pn at plus 1 is equal to Pn at minus 1 is equal to 0 for even n, and you can write down the first few Legendre polynomials. P0 is just equal to 1, polynomial of order 0, okay, it is equal to 1, it is 1 at 1 and 1 at minus 1. Okay. P1 is equal to psi or cos theta. Okay. This is equal to 1 at 1 and 1 at minus 1 at minus 1, okay, because it is odd n. P2 is equal to 3 cos square theta minus 1 by 2. Okay. Once again, this is equal to 1 at psi equals 1 or is equal to 3 psi square minus 1 by 2. Okay. So, this is equal to 1 at plus 1 and 1 at minus 1, okay, and so forth. Okay. So, you can get a whole series of these Legendre polynomials. So, finally, we have got t is equal to sigma, okay, n is equal to 0 to infinity a n r power n plus b n by r power n plus 1 p n of cos theta. As the solution for del square t is equal to 0, okay, del square t is equal to 0 in a spherical axisymmetric coordinate system. Our original problem was to solve the heat conduction for a sphere that is placed in a linear temperature field far from the sphere, okay, for a sphere that is placed in a linear temperature field far from the sphere. Now, we have got the solution. This solution is applicable both for the particle and for the matrix. Coefficients have to be determined from the boundary conditions. How do we determine these coefficients? We will continue that in the next lecture. I will see you then.